Hello everyone, my name is Cody Trevillian, and I'm from Oakland University. Today I'm here to pitch to you my recent work on temporal magnon-qubit Mach-Zehnder interferometry. This work is motivated by the necessity to improve our understandings of single magnon dynamics. On the left is a concept for a YIG-based single magnon source, and on the right is a detail of an on-chip fabrication method for YIG that achieves strong magnon-photon coupling rates. And so this combination of recent advancements may enable building such single magnon devices. And to utilize these single magnon states, it's important then that we understand how single magnon decoherence occurs, and therefore we need some sort of tool to study it. To study the decoherence of single magnons, we can take inspiration from the quantum optics community. So we can use something like a Mach-Zehnder interferometer to study the interference pattern and gain information about the decoherence process. So on the left you can see a system design for an optical Mach-Zehnder interferometer, and on the right is a measurement scheme. And so while a direct analog in the spatial domain would be possible, propagating magnons have shorter lifetimes than would be useful for study. So instead, with magnons, we can utilize interference in the temporal domain. How would this work? Well, in a typical Mach-Zehnder interferometer, we're studying photons with lasers. And so we have two beams that interact at certain spatial points. And by adjusting the lengths of the two arms, we can study the interference pattern at one or both detectors. However, in our temporal Mach-Zehnder interferometer, we're studying magnons with qubits. And so we have two modes that interact at certain points in time. And to do this, we can use short pulses of magnetic field. And so by shaping the pulses such that the frequency gap becomes small, we can controllably interact the two modes. Otherwise, the frequency gap would be large and the two modes would not interact and evolve freely. And so by adjusting the frequency gap and free evolution time, we can study the interference pattern that's generated. So in this case, both initial excitement and final detection occur via the qubit mode, and so we're never interacting directly with the magnon mode. On the left is a cartoon of the magnetic field dependence of the magnon resonance, and on the right is a possible system design. And so the system is described with a simple Hamiltonian of coupled resonators, where the resonant frequency of the qubit mode is this omega q, omega m is the resonant frequency of the magnon mode, and kappa is the coupling rate between the two subsystems. And the magnon resonance frequency depends on the magnetic field and can be controlled dynamically in time, while the qubit resonance frequency stays constant. So we can pulse the magnetic field such that the photon state of the qubit is cut in half. This means that we can effectively entangle the magnon and photon modes by realizing a magnonic beam splitter. Similarly, we can apply the same size tangle pulse operation again to unentangle the two modes. On the right, the interference pattern shown is generated by changing the free evolution time while fixing the frequency gap. So after initially exciting the qubit mode, we run our measurement scheme and detect the final qubit population. And in this graph, the horizontal axis is the free evolution time, and the vertical axis is the final qubit population. So the solid red line shows the measured qubit population, and the dashed gray line shows the average qubit population. We can also generate an interference pattern by changing the frequency gap while fixing the free evolution time. As before, we initially excite the qubit mode, run the measurement scheme, and then detect the final qubit population. And so in this graph, the horizontal axis is now this frequency gap, and the vertical axis is again the final qubit population. And so far, the interference patterns have not had any decoherence present. So let's consider two potential single magnon decoherence mechanisms. In amplitude damping, a magnon encounters some inhomogeneity and scatters into a phonon, and the energy is lost. And in phase damping, a magnon and a phonon scatter off one another, and the phase information is lost. These decoherence processes can be described by Lindblad jump operators, and so the gamma terms are the noise rates of the processes. And these Lindblad equations give you more detail in how these are mathematically simulated. So the interference patterns generated by changing the free evolution time turn out to be a lot more interesting. So we'll look at those, and we can clearly see that for amplitude decoherence, the average of the final qubit population changes as we vary the evolution time. This means that we can recover the decoherence rate from the average by some sort of curve fitting. And in contrast, for phase decoherence, the average of the final qubit population does not change as we vary the free evolution time. And so that means we have to use the maxima and minima of the qubit population for our curve fitting. But for a mixture of these decoherence, we can perform a combination of these curve fitting methods to separately recover the different noise rates. And while this might be more interesting to look at, we can also instead use a changing frequency gap, which might be easier to realize experimentally. Here, the interference patterns are generated by changing the frequency gap, and to recover the noise rates, we need only measure the maxima and minima of the qubit population. And instead of a curve fitting approach, we can utilize these nice and neat looking equations to recover separately the noise rates. And so this really is the sort of key punchline of this whole pitch, is that here are these equations, and we can go and measure our noise rates separately in our system using this temporal magnon-qubit Mach-Zehnder interferometry. So again, we proposed and pitched this temporal magnon-qubit Mach-Zehnder interferometry to study single magnon states, and we showed that it can be used to study different single magnon decoherence processes, and importantly, the scheme allows us to separately measure different noise rates. Thank you.